Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. Tonight, it's my pleasure to welcome my colleague John Ruhl, who's the Connecticut Professor of Physics at Case Western Reserve University and is a leader in the observation of the cosmic microwave background, the light from the early universe. But tonight, he's going to tell us about the physics behind global warming. Please welcome John.
Thank you. As I'm sure you're well aware, global warming is a topic that is of great interest to many people here on our planet. I've always been struck by how simple my view of the physics is of this effect, and how many people see it though as complicated. And so what I hope to do tonight is to give you a sense of the simplicity of the physics behind this, in hopes that helps you think about it and meet the global conversation. So a lot of what I'm going to be talking about tonight is based on some physics known as blackbody radiation. And what's important here to know is that all objects are glowing all the time. How much they're glowing depends on the temperature that object is, and also on how black that object is. So hotter things glow more. As you see with this little coil of wire here, the tip is very hot and it's glowing at both brighter, and it appears more yellow than the cooler stuff, which appears red. That is that its emission has shifted towards the blue. Cooler things glow less, and they glow redder or at longer wavelengths. So you can do a demonstration of this at home. I'll show you a demonstration I did this afternoon in my lab with a light bulb. This is a small incandescent light bulb, and if you adjust the amount of power going to it by turning a knob on a thing called a variac, if you put more electrical energy into a light bulb, the filament, it heats up. And as you can see, it starts out kind of dark and red, and it heats up, and it gets whiter and whiter, and a lot brighter. The energy coming out is equal to the energy going in. The energy coming out in light and heat is equal to the energy going in from the electronics. As you saw there at the very end, it turned very dim and very red as it got cooler. The physics of blackbody radiation has been understood very well since 1900, when Max Planck wrote down the mathematics and the physics that led to the curve shown here, where you can predict how bright an object is at a given wavelength just from its temperature. So here's our two curves showing what a 300 Kelvin blackbody looks like. 300 Kelvin is room temperature. By the way, I'll be using, a lot of times I'll be talking about temperature in terms of Kelvin, where 0 is absolute 0, and 300 Kelvin is room temperature. 273 Kelvin is 0 degrees Celsius, and the size of a degree Kelvin is the same as a degree Celsius. Okay, they're just offset, so that 0 degrees Celsius is 273 degrees Kelvin. The important thing that we're going to be using from the theory of blackbody radiation is actually this equation. This is the one equation that's going to be used over and over and over again in this presentation, which is the power that is coming out in light, like from that light bulb, is equal to a constant called sigma, the Stefan-Boltzmann constant, times the temperature in Kelvin to the 4th power. So if you know that filament and you know what its temperature is, you can tell how much light is coming out of it by using this very simple equation. You also need to know the area of the filament, because this is in units of watts per square meter, and so you'd need to know how many square meters that filament is to predict how much light is coming out. Temperature to the 4th is a very fast a function of temperature. It goes up fast as you change the temperature. Okay, now let's figure out why the Earth is the temperature that it is. We're absorbing sunlight all the time. Okay, the sunlight is coming. The sun, by the way, is a black body. It's emitting an awful lot like a black body at a high temperature, 5,000 Kelvin or something. And its sunlight is coming out to us, and it gets intercepted by the Earth. The Earth gets into equilibrium. In other words, it reaches a temperature and stays at that temperature because the amount of power it's getting from the sun is going to equal the amount of power that it emits in blackbody radiation. So we have to just figure out how much power is it absorbing from the sun, and then we can figure out how much power, we'll know how much power it needs to emit in blackbody radiation. So the yellow arrow there is all the sunlight, and the red arrows going every which way are the Earth's blackbody radiation going outwards. Those two powers have to be the same. So let's calculate the amount of power that the Earth is receiving from the sun, absorbing from the sun. First of all, you can go up in the upper atmosphere or near space, just above the atmosphere, and you can measure this. This has been measured, and what you find is that you get a flux of 1,361 watts per square meter from the sun. Now, not all of that gets absorbed by the Earth. In fact, we can tell that because spacecraft can look down and actually see the Earth. We know that there is light coming off the Earth. You see the ice sheets or the clouds are white, right? The oceans are blue. So therefore, there's different amounts of light that are actually being reflected by the Earth that allow us to see it. It's about 30% in total. But let's actually look at where that comes from, okay, that number that's about 30% total reflected. Different surfaces will reflect different amounts of the sunlight. So what you can see here is that fresh asphalt has what we call an albedo that is, here's the word albedo, and it's 0.04. What does that mean? That means that fresh asphalt is almost perfectly absorbing. It only reflects 4% of the sunlight. Green grass reflects 25%. Fresh snow reflects 85%. So we won't talk about it much in this talk, but the albedo of the Earth is an important feedback in global warming, where if we manage to change how much of the Earth is covered by bare soil versus fresh snow versus open ocean, if we change those numbers, we can change how much of the light is reflected back into space. Okay, the average for the Earth, as I mentioned, the average albedo is 0.3, which means that roughly 30% of the light is reflected back into space. Now we can do a calculation. Our calculation is that we take the 1,361 watts per square meter that come from the sun, that illuminate the disk of the Earth. The area of that disk is pi r Earth squared. And we account for 30% being reflected by saying 0.7 times 1361 times the area projected of the Earth, that disk. And what we end up with is 1.2 petawatts. 1.2 times 10 to the 17th watts. That's how much sunlight power is being absorbed by the Earth all the time. If you now average that over the surface of the sphere, including the dark side and everything, right, then you end up with a number that is equivalent to 240 watts per square meter. So it's all coming on one side, but if I average it over the whole sphere, I end up with 240 watts per square meter. Almost all of this ends up as heat on the surface of the Earth. If I put up a solar panel and I catch it, that power, and it comes in and I turn it into electricity, eventually the electricity gets turned into lights inside this room, which then get absorbed into the carpet or me, and we all heat up a little bit. Sometimes that sunlight will go and will hit a city, and it'll drive a convection current in the atmosphere, and those atmospheric currents will swirl, but eventually they turn into friction and they get dissipated as heat. You could power a windmill with those winds, and eventually still it would come into your house and it would turn on your TV and illuminate the wall and turn into heat. So all of this stuff eventually turns into heat on the surface. There are a couple small caveats to that. One is we can send spacecraft up on the dark side of the Earth and we can look down at the Earth and we see lights in cities. So some small amount of that energy actually just gets sent up as light into the cosmos. But that's a tiny, tiny fraction of the total energy that comes from the sun and dissipates onto the planet. So this is how much power the Earth needs to emit via blackbody radiation to be in equilibrium, to have power in equals power out. We can use that to calculate the temperature of the surface of the Earth, or at least the apparent temperature as seen by an observer out in space looking down at the Earth. So on average, the Earth has to look like a blackbody that satisfies this equation. 1.2 petawatts equals the surface area of the whole sphere times sigma t to the fourth, the Stefan Boltzmann law. What does that give us? Well, as I said before, sigma T to the fourth is 240 watts per square meter. So I can now solve for T. What do I get? 255 Kelvin, minus 18 degrees Celsius, minus 1 degree Fahrenheit. Now that's awfully cold, right? And we would be in deep, deep trouble if that was the temperature of the surface of the Earth, because most of the Earth would be frozen. We'd all be living in Antarctica, and we would be very unhappy. This is in fact not too different though than what the surface of Mars is like. Mars does not have a greenhouse effect, an atmosphere helping warm it up. So the surface of Mars, now Mars is a little farther away from the sun, so the sunlight is weaker, so the equilibrium is a little bit different, but Mars ends up at minus 60 degrees Celsius as an average surface temperature. So the fact that we have an atmosphere is what saves us from this fate, okay? And the greenhouse effect, really, the greenhouse effect is what warms us up a little bit above this and makes life possible. And what we're worried about happening in the future is not the instigation of a greenhouse effect from human emissions or anything like that. What we're worried about is a change in the greenhouse effect. So how does that work? Well, before we get there, I want to point out one other thing, which is that somehow the atmosphere is going to change the infrared equation, our emission, and allow the surface to get warmer. But we know that it lets the sunlight through. And here is, when we look at the Blackbody equation, what I've graphed here is the brightness or the amount of power coming in at a given wavelength for the sun, which is a 5,773 degree blackbody. And what you see there, and by the way, this there's a little chart down here that shows you where the visible wavelengths are. So those are about from 0.4 to 0.7 microns or so in wavelength. You may have heard of that as 400 to 700 nanometers if you've studied this before. But those are the wavelengths that are visible. The sun is visible. It emits a lot of electromagnetic radiation in the visible wavelengths. The Earth is glowing at much longer wavelengths because it is so much cooler. Remember the light bulb, as I turned down the power, it got redder and redder and redder. If I had kept turning it down, well, it gets redder and redder and redder all the way to the point where the wavelengths go beyond the red into what we call the infrared. So wavelengths that are longer than the visible over here in this direction, longer than the visible, those are called the infrared wavelengths. Because this is 255 Kelvin, which is not very different than 300 Kelvin, we call the wavelengths that are associated with black bodies emitting at those temperatures the thermal infrared, as I've noted up top here. So I will talk about the thermal infrared and the effect of the atmosphere on the thermal infrared. And one thing I want you to see here is that whatever happens with the atmosphere and the thermal infrared does not necessarily affect all this light that's in the visible regime, in the near infrared, these wavelengths that are around 1 micron, say, or 2 microns. Those can be affected independently of the physics. So the atmosphere can let the sunlight through while doing something interesting in the thermal infrared. So I'd like to pause there and take questions.
When you were showing the different rates of absorption, asphalt was 4%, and then it went on up from there. Just a question. Now, if we switched and asphalt, if we painted the lots white and the stripes black, would that make much difference?
Yes, it would. Yes, yes. White paint is actually much more reflective in the near infrared. And I'd like to tell you a little story, actually. One of the reasons that I got interested in explaining this type of physics to people was that I deal with it all the time in my work. One of the things that we do is build instruments that go up in stratospheric balloons, and they go up where there's almost no atmosphere. 1%, you're above 99% of the atmosphere. And one of the things that we have to do to keep our electronics and other parts of the balloon gondola from overheating is taking it and painting it white or covering it with white duct tape, because that has a much better reflection of the solar light, and it also emits better in the infrared. If you had an aluminum piece of metal up there that was exposed to the light, it would get really hot, and all your electronics would fry. So you're absolutely right that if we pave paradise and paint it white, we'll be fine.
That table of albedos that you showed, the lowest one on there was coniferous forest, isn't it?
Let's see. I'm trying to find it actually. Let's see. That was at the beginning. Okay. Coniferous forest. Yes. You must have been there. Okay.
Yeah. Okay. That's only 1% of the light is getting reflected, and asphalt was 4%, 4 times as much, and deciduous forest was 15%. And then where was green grass was 25%. What's the explanation for that? I know conifer forests, you're looking at needles. There's no big surfaces to reflect a lot of light.
Yes.
So a lot of it gets down and heats up the bark and the ground. But I don't understand the green grass and the trees. I mean, when you look at
I think you're pointing out something really interesting for two reasons, right? One is that when you want to build a light absorber, you don't want a flat sheet. A flat sheet it tends to have lots of, it only takes one bounce to get out and get back to space. So if you build something that has lots of corrugations in it like this, then you will have bounces that then, you have many bounces in order to get back out to space. And if each of those bounces absorbs half the light, pretty soon you've got almost nothing coming out. If you have lots of bounces. So I suspect that the conifer forest is benefiting from that in the sense that light comes in and it's bound to be reflected to the side and then the side and the side and the side. Another interesting thing about what you pointed out is that, and this messed me up for a while. I had to think about this for a while, but that when plants receive sunlight, part of the energy that hits the plant goes into chemistry, right? Goes into photosynthesis. It gets stored into the plant. And you might think to yourself, well, hold it, that's not heating up the surface of the earth, right? That's getting stored into chemicals. So maybe that doesn't count, right? And maybe that changes the energy balance. But in steady state, what's happening is that plants that did that exact same, that same chemistry 100 years ago, or a year ago in the case of grass or something, are decomposing. And those plants that are decomposing are releasing that chemical energy back. And the only exception to this is if you take plants, lots of ferns, and then you somehow bury them and you turn them into coal and oil and stuff like that, and you store the energy of the sunlight for underground. So if you sequester the energy, then it doesn't have to be in this energy balance, right? But on average for plants in our time, the decomposition is balancing out the photosynthesis, unless we change things.
Thank you for joining us. You've been watching Dr. John Ruhl discussing the basic properties of the light that comes from glowing objects, called blackbodies. For more information on the Origins Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Ruhl discussed the basic physics of the greenhouse effect and how burning fossil fuels warms the Earth. Now, back to the talk.
So now I'm going to present to you a simplified model of the greenhouse effect. Okay? And this is simpler than what you will read in some fancy climate report, but I think it gets the physics across. Okay? What we're going to do is we're going to model the atmosphere, all the greenhouse gases that warm us up from that frigid 255 to something that's more like 15 C, 255 Kelvin to 15 C. We're going to model it as a single layer of perfectly absorbing gas that covers everything in the thermal infrared. Okay, it does not block the sunlight, because this gas is special, because it's black in the thermal infrared, but lets light through in the solar spectrum. Okay? So the sunlight is coming through with this 240 watts per meter squared averaged over the entire surface of the sphere. Okay? Now, this layer here right? This layer here, in order to have thermal balance, because it's black, the ground, the green light right here, wants to emit up here, but that light does not escape into space. The green arrow gets stopped by the blue layer. And it's this amount of energy, the 240 watts per square meter, that is being emitted from the outer part of the atmosphere that is actually keeping the Earth in thermal balance with the sun. Okay? So this actually does come to the temperature that we calculated previously, 255 Kelvin in thermal balance. And what I can do is I can then look at, well, what about the surface of the Earth, if it's a black body as well? Well, it's getting 240 watts per meter squared from the sun, but this layer of atmosphere up here, it actually emits both outwards towards space and downwards towards the Earth, another 240 watts per meter squared. So the Earth, that green grass there, which is a black body, is getting 480 watts per meter squared. Again, I can use this Stefan Boltzmann law, sigma t to the fourth, to solve for the temperature of the surface of the Earth in this model, and what I find is that it's 303 Kelvin, 30 C, nice and warm, toasty. It's actually warmer than the actual surface of our Earth on average, right? But it's a simplified model. So this is how greenhouse gases work. They are, of course, not a perfect absorbing thermal infrared layer, right? They're not quite perfect, right? So the temperature change is not quite as big as this. Okay, nonetheless, I could still go further with this model. I can ask, what happens if I double the amount of absorbing gas in the atmosphere? And I'm going to do it in a very special way, okay? I'm going to do it as a separate layer that is only talking to the other layer, only giving energy to the other layer via infrared radiation, that thermal infrared radiation. Okay, so they're not mixing, there's no convection in the atmosphere. This is just a simple radiator. Okay. Again, the outer layer has to give that 240 watts per square meter, so it comes to the same temperature as before. But, oops, hold it, I wasn't supposed to go forward there. We'll go here. Here we go. So we have the 240 watts per meter squared going to to space for that layer. This layer, the pink layer, is between a cold thing at 255 Kelvin and a warm thing that was at 303 Kelvin before. I think it's pretty clear that that thing that's in between a warm thing and a cold thing is going to want to come to an intermediate temperature, right? If it's coming to an intermediate temperature, that means that its blackbody radiation, its sigma t to the fourth, is going to be greater than 240 watts per square meter. What does that mean? That means that the surface of the Earth now is absorbing the sunlight, which is 240 watts per square meter, and this extra stuff, which is more than 240 watts per square meter. In other words, the infrared power, or the total power, sunlight plus infrared stuff on the surface of the Earth just grew. We stuck in a new layer of gases, and the amount of power hitting the surface of the Earth grew. What does that mean? It means it needs to heat up, right? So this temperature has to go up. 303 Kelvin has to increase. Now we can solve this very easily, just writing down a few equations. The equations actually aren't that hard, and so I will actually write it here. The amount of power that's hitting the surface of the Earth right now has to be 240 from sunlight. This power that this needs to radiate will be 480 watts per meter squared in order to send that all up to this layer, which is losing 480 watts per meter squared. So these things balance. The pink that I've circled balances the two blue ones and keeps that top blue layer at the same required temperature of 255 Kelvin. And if that's emitting 480 up, it's also emitting 480 down. So the power incident on the surface of the Earth is 240 plus 480, or 720 watts per meter squared. And I can solve that for the temperature of the Earth, and I get 336 Kelvin. So in this very simple model, what has happened is that I just doubled the amount of perfect absorbing layers, and the surface of the Earth temperature went up by about 30 degrees Celsius. Okay? All right. this is a very simple model, but it recreates some of the stuff that we know about the atmosphere. So here is the US standard atmosphere graphed on a scale where we have altitude in feet on the y-axis right here. And we go from 0 to 100,000 feet. When we fly our science balloons, they actually go up to about 110, 120,000 feet. And on one graph, we have the temperature of the atmosphere as you go up. And as you can see, it goes from being fairly warm, 15 C or something like that, to very cold, minus 50, minus 60 C. And by the time you're up here, where it's maybe starting to warm just a little bit, you've got almost no density to the atmosphere. Okay, you can see that you're above almost all of the molecules in the atmosphere. So we really care about the bottom layers of the atmosphere, and the fact is that the temperature is going down as you go up, just like it did in my model. Right? We had an intermediate layer that came to an intermediate temperature, an upper layer that got really cold, similar to the real atmosphere. And that's not to say that my model is perfect, is wonderful, has all the physics in it, but it has some simple physics and it recreates the basic idea. Okay. When we look at the actual spectra of stuff that's passing through the atmosphere, we can show that in a complicated graph here. So I want to take a couple minutes to go through this graph. The top one shows the solar spectrum, so that 5,500 Kelvin black body right there, and then some of that is absorbed. It's not true that the atmosphere is completely transparent at those wavelengths. Some of it is absorbed, about 70 to 75% gets in. Some of it is reflected by clouds and things like that. If the Earth was sitting at 310 Kelvin, say, this black line right here, it would be emitting that spectrum, but not all of it would get to space. In fact, the blue curve is what's left after all of the thermal infrared blocking constituents of the atmosphere. So this next graph right here shows what percentage, as it travels through space, or through the atmosphere, what percentage of the light at a given wavelength gets through. And what you see is over here in the visible, lots get through, and in fact it's just the inverse of the red curve, sort of. And you see that here in the thermal infrared, an awful lot gets blocked. Okay, you can see that very little out here gets blocked, or gets through. Only in that one little window does it shine, the surface shines straight through to space. In this window right here, where the surface shines straight through to space, my model is completely not right. Okay, because there is no black layer between the Earth and space in that case. Where none of it gets out to space right here, where the atmosphere is completely opaque, my model may have something to say. Right? My model may make some sense because there is an absorbing layer between us and space. Now, if we look at the constituents of the atmosphere that are actually making up all this absorption, and by the way, if a molecule is absorbing at a certain wavelength, it's also emitting blackbody radiation at that wavelength. That's one of the laws of physics. If it absorbs, then it has to emit. What you see here is that water vapor is a very effective greenhouse gas. Okay, so water vapor is absorbing a lot of the thermal infrared. Carbon dioxide is actually the one that I'm gonna concentrate on, so I want to circle that one. Carbon dioxide has one particular absorption feature that's very strong in part of the thermal infrared. You may have heard of these other greenhouse gases like methane and nitrous oxide. I'm not going to talk about them. Of course, they can be important as well. If I look at that carbon dioxide feature and I ask, how much of the wavelengths in the thermal infrared does it absorb? What's the fraction of the spectrum there? I do this completely by eye. I didn't do it numerically at all. Okay, so I'm just winging it here. I'm going to say that it's about 1/10 of the spectrum. You may come up with something different, and that's okay, right? But if we go with 1/10 of the thermal infrared, then remember in my model, when I doubled the absorbing layer at all wavelengths, I got 30 C of temperature change at the surface of the Earth. So I'm going to say here, instead of 30C, I get a tenth of that, because I'm really only adding the extra black layer in 10% of the wavelengths, which tells me that if I double the CO2, I should get about a 3 degrees Celsius change at the surface of the Earth, roughly speaking. I'm doing back of the envelope physics here. Don't quote me to 2 significant digits or something like that. Okay. Well, I want to figure out now, if my model says that we've doubled, if we double the CO2 layer, we'll go up by 3C, right? I want to know how much have we done, and does it agree with how much emissions we think we've had over time? How much fossil fuel we've burned, okay? And you can go online and you can look up the global fossil fuel consumption as a function of time. And this is the amount per year in various fossil fuels that has been burned up through 2016, okay? And then you can take this particular graph has energy on the y-axis. You can convert that to tons of fuel, just knowing how much energy you get out of a ton of various fuels. And it's a little bit different for these 3 different kinds of fuels. But what you'll end up with is a number that says that we have burned over the course of humanity, because going back from 1800 to 0 AD is like almost nothing, as you can see here. We've burned about 400 gigatons, 400 times 10 to the 9 tons of fossil fuels in this time. Okay? So we can figure out how much CO2 we get from burning 400 gigatons of fossil fuels just by doing some simple accounting. Okay? We understand the chemistry of burning, and here's one of the reactions that's important. Coal, I'm going to model coal. C is not for coal, C stands for carbon. So I've got carbon and I combine it with oxygen, which is sort of the definition of burning, and I get CO2 out and some energy, okay? Notice that if I put in 1 gram of carbon and burn it this way, I get 3.7 grams of carbon dioxide out, okay? That's a 1 to 3.7 ratio. If I burn natural gas, which I'm going to write here as methane, which is the predominant component, if I burn 1 gram of methane, I get about 2.75 grams of CO2. By the way, that 1 gram of methane actually gave me more energy as well than burning coal. And this is one of the reasons why people think burning natural gas is good in terms of CO2 emissions. If I burn gasoline, which I'm going to write here as octane, I have 1 gram of that gives me 3.09 grams of CO2. In the spirit of simplicity, I'm going to say that for every 1 gram of fuel we burn, we get 3 grams of CO2 out. Okay? So 400 gigatons of fossil fuel turns into something like 1,200 gigatons of CO2. Now, how much carbon dioxide measured in terms of the things that we may read about, which is the parts per million in the atmosphere, how much does that change? If I stick 1,200 gigatons of CO2 into the atmosphere, okay? Well, that turns out to be very simple to calculate as well. Right? What we do is we figure out how much the atmosphere weighs by taking the surface pressure, which is 15 pounds per square inch. That's the pressure, pressure at sea level. And we multiply it by the surface area of the sphere of the Earth, which I won't bother writing out here. And what you find out is that the atmosphere weighs 5 million gigatons. Okay, it's really fun being a physicist because I can play with numbers like this and just, wow, the atmosphere weighs 5 million gigatons. My kids would love that. They would want to make up a cartoon about it. All right. If I take my measly 1,200 gigatons of CO2 that I stuck into the atmosphere and I do the division, I find out that I have 240 parts per million by mass. Okay, because I was doing mass over mass. Now, CO2 weighs more as a molecule than O2 or N2. Okay, and so when we go to compare to the numbers that we hear on the news about parts per million, that's parts per million by volume or parts per million by number count of the atoms. And so if we account for that mass difference between CO2 and N2 and O2, what we find out is that we have about 160 parts per million by volume. In other words, I just go to the Energy Information Agency and I look up how much fossil fuels have we burned over time. I say, how many tons is that? And boom, I can tell you that this is how much carbon dioxide went into the atmosphere from our burning. Okay. So the actual increase as measured has been a little bit less than that, actually, 120 parts per million by volume, because an awful lot of the carbon dioxide actually goes into the oceans, gets absorbed in the oceans, and that's about a factor of 2, so which is close enough for our case here. And that, of course, causes other problems like ocean acidification, which I'm not going to talk about because this is a talk about global warming. Right? Okay, now that we know that humanity has stuck in enough carbon dioxide to increase the CO2 by, we've increased it by 120 parts per million. That's about 40% over the pre-industrial values, okay? So now, let's just say how much temperature rise do we expect in our simple model? Well, in our simple model, doubling the CO2 would have led, remember, to 3 degrees Celsius change. We haven't doubled the CO2, we've increased it by 40%. So 40% of 3 is 1.2 degrees Celsius. A fancier model, if you go look at a climate physics book, or you go to the IPCC reports or something like that, they will model delta T as this equation with a natural log in it and some uncertainty in the coefficient, but they will say something like a factor of, or an amount of delta T is about 1 to 2 degrees Celsius expected from this much CO2 rise. And the actual observed warming is about 1C. So this very simple model where all we did was some radiative physics, using physics that was left over from, not left over, vibrantly, excitingly used since 1900, right? We actually get a number that is motivated by simple physics and agrees with the observed warming, and the amount of CO2 increase makes a lot of sense. So the summary to this point, I would say, is that greenhouse gases like CO2 create these insulating infrared black layers in the atmosphere, right? And that humans have burnt more than enough fossil fuels to account for the increase in atmospheric CO2, and that the observed increase in CO2 is expected to produce, just by envelope napkin style physics, the observed warming that we've seen. So global warming should not be surprising to anyone, right? The physics is very simple, and using that basic physics and some facts about our fossil fuel use tells you that this much warming should roughly be happening. And I'd like to stop there and ask questions. Or not ask questions, I'll try to answer them.
Could you put that black layer slide on again? As an engineer who's used to doing heat balances,
you mean this one?
To quibble with it. Way back at the beginning of part 2.
Oh, okay. Oh, way back at the beginning of part 2. Let me see if I can get there. This one?
That's the one.
Yeah.
You've got the Earth, first of all, passing the sunlight 240 watts per square meter.
The Earth absorbs it, yeah. The Earth absorbs it.
240 watts per square meter to a perfectly absorbing layer. I believe only half of that is radiated to space. The other half is radiated.
Which way are you talking about? The blue layer or the pink layer?
Layer?
Okay, the blue layer is radiating upwards to space, 240. It is also radiating downwards, because if you have a black sheet, it radiates in both directions by this amount.
Exactly.
Yep.
The question is, it's radiating 480.
That's right.
Is what you have, not 240. It radiates 240, but it's 120 up and 120 down.
No.
It doesn't change the conclusion.
No, that's incorrect. It actually radiates, if you have a black surface, it actually radiates in both directions by this amount. Sigma T to the 4th
you have an energy balance that's not working here.
No, I do actually. Look at this. This is 240 plus 240 being lost by that layer. This is 480, double that's coming into that layer and being absorbed. This layer is losing 480 up and 480 down, it's actually getting 240 from this one plus 720 from this one, and you'll see that that balances.
Hypothetically, suppose you had 6 of them, would you get 6 times 240?
You would get a very large number.
No,
You would actually, and in fact, this is the basis behind super insulation in cryogenic vessels.
Yeah.
We stick, if you have 2 surfaces, and then you start sticking multilayer insulation in there, you go down, the power load on the inner surface goes down by 1, the colder surface goes down by 1 over n plus 1.
But you can't radiate twice as much energy as you're absorbing.
I'm not, no, this is in balance. We can talk about it afterwards.
If you're absorbing 240 radiated from the Earth, you can't be 240.
The Earth is radiating, the Earth is getting 240 from sunlight plus 480 from this layer. I'd be happy to talk to you afterwards.
We hope you've been enjoying the Origin Science Scholars Program with Dr. John Ruhl. Dr. Ruhl is Connecticut Professor of Physics at Case Western Reserve University, a leading scientist in the observation of the microwave radiation from the early universe, and a fellow of the Institute for the Science of Origins. In the second part of our talk, we learned how our society's use of fossil fuel has added carbon dioxide to the atmosphere, and how that carbon dioxide acts like an insulating blanket to warm the Earth's surface. In our final segment, Dr. Ruhl will examine how per capita emissions of greenhouse gases must decline to prevent global disaster. Now, back to our talk.
I'm going to go on now and I'm going to talk about things that are a little longer term, blue sky thinking, okay? So, looking at the past though, the energy production in the United States, what you can see is that it's been rising quickly for a long time, okay? For this covers a little over 200 years. You can also see that it's dominated by the fossil fuels. There's a little bit of nuclear down here, and there's a little bit of renewables, right, that are turning on, and of course we're all excited about that. But the fact is it's dominated by fossil fuels, and it's been rising precipitously. And if I put this now on a different kind of graph, where instead of showing a linear axis on the y-axis, I show factors of 10. This same idea here shows that looks like kind of a straight line on this graph, and that the red line right there is a growth of 2.9% per year. It's growing by more than a factor of 10 every 100 years. Okay? Now, I want to note that the solar power that was getting absorbed by the Earth that we calculated early on, that was 10 to the 17 watts. We are using a number here, whoops, no, sorry. We are using a number here that is approaching 10 to the 13 watts. 10 to the 13 is a lot smaller than 10 to the 17. I am surprised that it's actually 0.01% of the solar power that is incident on the Earth. That's pretty amazing. And that's just in the United States. A crucial fact of what I'm going to be talking about here is that, as I discussed before, almost all of the energy use that we have, everything that we do, ends up as heat here on Earth. Okay, all the cars we drive, all the electricity we make, a little bit that turns into light that goes out into space, but not much. Almost all of it becomes heat here on Earth. Okay, and the question is, what happens if this number keeps on rising in this manner? Okay, well, I can look at this number and project it into the future, rising by a factor of 10 every 100 years, and of course, eventually I'm gonna get to really ridiculous amounts of power usage. So on this x-axis here, I have years from now. Okay, and as you can see, it goes from 0 to 2,600 years from now. That's a long time. Okay, but the usage right now is down here at 0 years from now, a little under 10 to the 14 watts that we're using. And as I look forward in time. Now, it's always a little bit funny to look forward in time because we all know that we're going to be gone. But if I can compare it to backwards in time, and so, for instance, the Industrial Revolution was, 100, 200 years ago. The Renaissance was 400 or 500 years ago, right? The Dark Ages were, 12, 1300 years ago. So it's in our historical memory, these kinds of time spans, right? So I can look forward and I can ask, okay, can we keep on this track with energy growth, energy use, energy production for a long, long, long time, right, in terms of human civilization. And the answer is that no, it quickly gets ridiculous. If you ask how much solar power hits land that you could convert to electricity with 20% efficiency if you covered all the land mass of the Earth, then you'd end up with, roughly speaking, 10 to the 16 watts available. Okay, so maybe we can imagine all living under solar panels, okay? If you ask, well, what if I covered the entire surface of the Earth, right, with solar panels and used all that electricity? Well, okay, that would be great. Okay, that's that. But now, if I have some other way other than solar power of generating that electricity, so let's say that I actually use nuclear power, and I generate that 10 to the 17 watts. Now I have a problem, because I have 10 to the 17 watts coming in from the sun that's getting absorbed on the surface of the Earth, and I'm generating 10 to the 17 watts with nuclear power, say, and it's getting dissipated as heat on the surface of the Earth. So the Earth's surface now has to come into energy balance with both of those inputs. I've doubled the amount of energy being dissipated on the surface of the Earth, so therefore it has to get hotter. If I keep on this track, what we see here is, well, eventually I get 1,300 years, 1,400 years from now, I'm actually using, civilization would be using the entire energy output of the sun. Some people talk about Dyson spheres, a big surface around the sun, catching and all. And if I keep on for 2,400 years, which isn't too much far in the future, more than the Roman Empire was looking backwards, then I'm using all the energy output of the entire galaxy. Good luck with that. Now, let's talk about the temperature, though. I mentioned here in terms of if we use nuclear power to generate 10 to the 17 watts for us, and then dissipate it as heat on the surface of the Earth, then something's going to get interesting. And here's what sigma t to the fourth looks like in terms of time from now. Okay? So right now, we are in Celsius. We're sort of at around 15 C, average temperature of the surface of the Earth. If I take that energy input looking forward over time, in 350 years or something like that, the surface of the Earth would be at 98.6 degrees Fahrenheit, 37 Celsius, or whatever it is. In not too much longer after that, we'd be boiling the oceans. I think we'd stop at that point, right? But if we kept going, we'd get to the point where all your forests and paper would burn, right? And eventually so would everything, all your cars and everything. And eventually you're just like the sun, okay? Less than 1,000 years from now. So I agree, this is looking way out into the future, and it's kind of crazy seeming, right? But at least, I think it makes you think a little bit differently about what our trajectory should be over the course of the next few centuries. Okay? Now, one of the things that drives that curve of energy use increase in the United States is the population growth of the United States. So you can see here that from 1800 to 1900, roughly, the population of the United States went up by a factor of 10. From 1900 to 2000, it went up by about a factor of 3. So population growth is slowing. If I take the energy use of the United States and divide it by the population, I get a number which is the amount of energy per person that's being used. And that's actually a surprisingly shallow function. In other words, it's not rising super fast. Over the course of the last 200 years, I find it amazing to see that our energy use per person has only gone up by a factor of 3 or 4. In other words, most of that great increase that was projecting forth into the future centuries, or at least a lot of it, was being driven by population increase, not by energy intensity. And yes, we have a whole world out there where there's billions of people who would benefit from using more energy, right, who could come up to closer to our standard of living by using more energy. But we can hope that we can do that by taking their energy use from something like maybe we had in 1800 to what we have now, factors of 3 or 4 per person, not factors of 100. I find that actually a little bit heartening, that maybe a little bit of investment of energy brings people up to our standard. Now, the world population is going up, and this shows the UN's most recent prognostications on what the future of the population of Earth might be. And what you can see is that there, too, it's expected to slow. The population growth is slowing. Roughly about a factor of 5 in 100 years between 1950 and 2050, then a factor of 1.5 in 100 years between 2020 and 2120. But, of course, there's a large uncertainty in exactly what that is. So I think when I think about the future of energy use on this planet, I guess I'll be long gone. But if we keep on that growth curve of a factor of 10 every 100 years, we will, in not too many times 100 years, we will run into real problems that is independent of climate change. It's just about dissipating the energy on the surface of the Earth. That is a little bit mitigated, my worry about that. Not that maybe I shouldn't be worried, but I worry for my kids' that the population growth is slowing down. So we'll have even more time to deal with that fact. So that's all to say that I think that to review everything I've said here, global warming I view as the result of simple physics. To avoid the greenhouse gas problem, right, we will need to think about the population changes. As the population goes up, we're gonna have more trouble. But of course, we want to focus on the emissions per capita. So we don't expect the total emissions to go up by a factor of 10 every 100 years. Okay, now this is of course built into the models of the IPCC and things like that. But then thinking even longer term, to avoid what I would call mega warming in the next 500 years, we have to think differently about what drives prosperity. If you listen to Washington right now, not that I recommend it, but if you do, then what you will hear is everybody saying that economic growth is necessary, and nobody asks the question of whether economic growth has to be tied to energy growth. And at some level, it seems like it probably does, but that's a question that one could discuss and debate. And I would hope that we eventually get politicians and other people thinking about prosperity being driven by something other than energy growth, at least, and that this would be a good thing to start thinking about now. And in fact, there are people, a very small minority of economic voices, who are thinking about no growth economics. That's a phrase that's interesting to look up, and trying to think about what does it mean for a society to flourish without continual economic, perhaps GDP-labeled growth.
So you're saying that use of solar energy and wind energy, although better, will still be a problem because it's going to, just using that energy is going to contribute to warming the Earth?
I didn't say exactly that. Because in the energy balance equation, if a ray of sunlight comes in and gets converted by a solar panel with 100% efficiency into electricity, then that ray of sunlight did not heat up the Earth then, it will heat up the Earth later. So solar and wind energy is similar in the sense that there's energy by the sun that is heating up different parts of the planet differently, and therefore causing the wind. And so that eventually, if you just let the wind go, it will eventually dissipate against rock faces and friction and that kind of thing, and there will be heating. But if you get to use it for your electronics, great. So that's a zero-sum game, I would call it.
But what about nuclear then?
Nuclear is something where we are taking the nuclear energy in the atoms and we are choosing to dissipate it as heat now on the surface of the planet. And so that is different, right? That is a new energy input to the surface of the planet.
Okay, so nuclear is out, wind and solar.
In this long-term, many hundreds of years thinking, if we grow energy by use of nuclear, that's a problem. Solar has a limit. There's only 10 to the 17 watts that we can catch on Earth.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.